Okay, let's dive right into this explainer. Have you ever stood on a beach, looked out at the ocean, and just wondered what lies just beyond the curve of the Earth? Well, for decades, military engineers have faced that exact same problem, but obviously on a massive, high-stakes scale. Traditional radar simply cannot see through the curvature of the planet. But what if, instead of trying to look through the Earth, you could use the sky itself to see thousands of kilometers over the horizon? It sounds like sci-fi, right? But today we're unpacking a groundbreaking piece of research on a technology designed to do exactly that. We have a pretty clear roadmap for today. We'll start with the actual radar need, move on to the skywave solution, explore the sheer chaos of the ionosphere, and then we'll unpack the multi-static architecture and real-time sounding tech that brings the whole shebang together.
All right, part one, the beyond horizon radar need.
Let's start by defining exactly what system we're looking at today and why it is considered such an absolute game changer in electronic warfare. We're talking about the O-MSRS. Now, that stands for Over-the-Horizon Multi-Static Backscatter Radar System. It's a mouthful, I know. It operates in the high-frequency band, specifically between 3 and 30 megahertz. And the absolutely crucial point here is that the system is designed to systematically identify targets way, way beyond national borders. Historically, to see over the horizon, militaries had to launch those incredibly expensive airborne radar planes, like AWACS. Well, the O-MSRS is actually projected to be a highly effective ground-based replacement for those airborne systems. So what exactly is it looking for? The literature highlights that this system targets modern, super elusive threats. We are talking about unmanned aerial vehicles, UAVs, and tactical ballistic missiles. Because traditional line-of-sight radar shoots straight out into space as the Earth curves away beneath it, it leaves us completely blind to low-altitude, fast-moving threats at long ranges. The O-MSRS solves this by securing a massive radius. We're talking 1,500 to 2,500 kilometers from a country's borders. Moving right along to part two, bouncing waves off the sky. Okay, this is where the physics gets really cool. How do you actually bend a radio wave around a spherical planet? Ground waves try to follow the Earth's surface, sure, but they lose energy super quickly and just fizzle out. To get true distance, engineers use what are called sky waves. They literally shoot high-frequency signals straight up into the atmosphere, specifically targeting the ionosphere. Now, the source research notes that while the E layer, which is about 110 kilometers up, has some effect, it's really the F layer, sitting way up at 300 kilometers above the Earth, that does the heavy lifting. It acts like a giant atmospheric mirror, refracting the radar signal and bouncing it back down to the surface, completely bypassing the curvature of the Earth. By angling these waves with precision, engineers can essentially illuminate a massive target area. Think of it like shining a flashlight at a mirror on your ceiling just to light up the next room. This brilliant workaround allows the radar station to sit safely, deep within its own territory, while effectively scanning a concentrated grid up to 3,000 kilometers away. Which brings us to part three, the chaotic ionosphere challenge. Here's the catch, right? Relying on the open sky as a precision mirror comes with a massive, mind-bending complication. The ionosphere isn't made of solid glass. It's this dynamic, almost living layer of the atmosphere. The concentration of electrons up there is what actually bounces the radar waves, but that concentration shifts wildly. I mean, it's affected by the 11-year solar cycle, the seasons, geography. In fact, the electron density drops dramatically just moving from daytime to nighttime. So that mirror we're relying on, it is constantly warping, thinning, and thickening. Because of this constantly shifting medium, your standard single-station monostatic radars face an absolute nightmare of errors. The source text outlines how this dynamic environment makes the radar highly susceptible to intentional electronic jamming. Plus, something as random as a literal meteor trail can create interference. You also get multipath propagation errors, which basically means the signal bounces off multiple shifting layers of the sky and returns at slightly different times. That creates ghost images and severely reduces radar accuracy, especially at night. So, this brings us to the ultimate engineering hurdle. How do you stabilize a radar that relies on a chaotic, shifting sky? How on earth do you implement electronic countermeasures to turn this blurry, unreliable atmospheric mirror into a pristine surveillance tool? Well, let's look at part four, multi-static O-MSRS architecture. The answer to that incredible physics problem lies in the M of the O-MSRS, multi-static architecture. Instead of having one giant dish that both sends and receives, which is what we call monostatic, the O-MSRS physically separates the transmitter from multiple decentralized receiver stations. So the transmitter blasts the skywave, it bounces down, hits the drone or the missile, scatters back up to the ionosphere, and then bounces down to several different receiver arrays spread out across totally different geographic locations.
This separation provides a huge technical advantage. See, in a traditional monostatic radar, the system blasts a massive pulse of energy and then has to briefly shut down its receivers, literally close its eyes for a split second, so it doesn't fry its own circuits. That creates a tiny window of time called the pulse recovery time, where the radar is totally blind. But with a multistatic system, the transmitters and receivers are far apart. The receivers are always on, zero blind spots. The data from all these separate receivers is funneled into a central processing unit concurrently, taking multiple blurry pictures from different angles and combining them into one ultra-sharp, real-time image of the target.
Next up, Part 5, Real-Time Ionosphere Sounding. Okay, so physically separating the stations and co-processing the data is amazing, but it's only half the battle. We still have to deal with the fact that the ionosphere itself is constantly changing. We need to map that chaotic sky in real time. To find the absolute perfect frequency to use at any given millisecond, the O-MSRS doesn't just cross its fingers and guess. It actively probes the atmosphere using 3 specialized sounders. The vertical incidence sounder shoots straight up to measure the ionosphere directly above the station. The oblique incidence sounder measures the condition of the sky across multiple diagonal paths. And finally, the backscatter sounder measures the actual power of the returning echoes based on range and frequency. And all of these sounders, they feed their data into the system to produce what's called an ionogram. Think of this as a real-time, highly colorful topographical map of the atmosphere's electrical layers. By constantly updating this ionogram, the O-MSRS can dynamically adapt its frequencies on the fly. If one layer of the sky becomes too chaotic or gets actively jammed by an adversary, the system instantly reads the ionogram map, calculates a new optimal frequency, and shifts the radar wave to a clearer path. It outsmarts the chaos of nature and the jamming of enemies, all at the exact same time. Finally, let's wrap up with Part 6, the future of surveillance. Let's bring all of this together to see what this incredible marriage of atmospheric physics and multi-static engineering actually means for modern security. When you combine the skywave bouncing, the elimination of blind spots through multi-static receivers, and the real-time atmospheric mapping of the ionograms, you get a massive, uninterrupted detection radius. We are talking about a secure coverage zone stretching 1,500 to 2,500 kilometers out. You can detect low-flying, stealthy UAVs, or fast-moving tactical missiles while they are still incredibly far away, offering precious minutes or even hours of early warning. And this technology isn't designed to just sit in a silo by itself. The research specifically emphasizes that the O-MSRS is highly capable of seamlessly coordinating with massive established defense networks. For example, it can feed its over-the-horizon data directly into the NATO Air Command and Control System, or ACCS. It literally takes localized data and turns it into actionable intelligence for an entire allied network. What we've seen today is honestly a perfect example of how limitations drive profound innovation. When engineers couldn't look through the Earth, they learned to read and manipulate the chaotic layers of the atmosphere to look around it. So as electronic countermeasures continue to evolve and threats become faster and stealthier, it leaves us with a fascinating final thought. How will our adversaries attempt to hide in a sky that we can now read, adapt to, and utilize like an open book? Thanks for joining me on this explainer, and I'll catch you on the next one.